Okay, hello everyone. Welcome to our fourth video of the number series. For today's video, we're gonna solve the problem in the chapter 4, which is about congruence. And let's jump right in, shall we? So the first question, we're gonna find the least residual of 1492 under modulo number 4, 10, and the 101. So basically you just take this number divided by this and you take the remainder. Well, very easy. And number 2 is just similar kind of question, so there's no need to explain anymore. And question number 3. Prove or disprove that if A is congruent to B modulo M, then A squared is congruent to B squared modulo M. And this is true because if A is congruent to B, then M is a divisor of A minus B. And basically number 2, A squared congruent to B squared, the saying that if asking us if M is a divisor of this, which is yes, because A minus B has a factor of M, which is true. And number 4, if A squared and congruent to B squared, then A is congruent to B or minus B. This is false. Well, this is true, but the reverse might not be true, because let's take this as an example. So A squared and B squared, they does congruent to 1, and but A is not congruent to B or its inverse, so this is not true. And for 5, finding all M such those congruent exist. Okay, so M must be a divisor of this, and after we simplify, we get 710. And all of the factor of 710 is here. So M could only be those numbers. And similarly, for question number 6, the value of M could be those. Question number 7. If K is congruent to 1 modulo 4, then what is 6K plus 5 congruent to? So we just sub in K equals to 1 and it's equal 11, and then we divide the number by 4 and we take the remainder, we got 3. Question number 8. Show that every prime except 2 is congruent to 1 or 3 modulo 4. We know that every prime number except number 2 is odd, because if a number has a factor of 2 and it is not number 2, then it is a composite number. Therefore, those two forms is getting eliminated. We have only number 1 and the third one exists, which correspond to congruent 1 modulo 4 and 3 modulo 4. Okay, question number 9. Show that every prime except 2 and 3 is congruent to 1 or 5. Well, very similar logic. We just rule out the multiple of 2 and multiple of 3. And that's all we have left, which is the only 2 possibilities. And next, question number 10. What can be the prime congruent to modulo 10? Well, this one is very long, and I'm just going to show you guys the answer. So it should be 1, 7, 11, 13, 17, 19, 23, 29. And if you read the chapter 9, I believe, of the book about Euler's theory and the function, And you're gonna know how much exactly number are co-prime to the number 30. And there's a formula for that, but for now you don't need to worry about that. After you read the chapter 9, you're gonna think those things begin to make sense, so don't worry too much. And let's just move on with our question. Question number 11. So we got a multiplication and the result have a 1 digit missing, and we're gonna figure out the number without actually calculating this multiplication here. It's going to take a long time and effort, and there's a smarter way if we just want to know this missing digit. We know that those two numbers are equal. That means that they are both congruent to the number of 9. No, they are both congruent to each other under modular 9. And we're gonna check the modular 9. A number's remainder of modular 9 is congruent to the sum of the digit. And this number has a sum of digit congruent to 5. And this has the sum of the digit congruent to 7. 5 times 7 is 35. It's congruent to 8. We know the adding of those long numbers of this result here should result in a number that's congruent to 8. And this mysterious number plus 2 is equals to 8. And we figure out x is congruent to 6. And we know that for a digit, it could be only between number 0 and to the number 9. And since it is congruent to 6 modulo 9, and we can deduce that it is only possible that x equals to 6. And next, question 12. Show that no square has its digit to be 2, 3, 6, and 7 and 8. Well, we can make a table and test. So those are the form of the square, and I'm just making a list, and this number n is like the number that's tailing the 10k. For example, this one is 0, this one is 1, and we make a table and we find this no 2, 3, 7, and 8. And next question. Well, here sorry, I'm just flipping the page. Yeah, just okay. Here we go. We are having a little accident here. You see the paper is not very perfect because I was using my eraser, and I'm using too much force when I'm erasing my wrong answer, and this is my bad. Notebook, I hope you forgive me for that. Yeah, let's take a look at the question. Just don't mind this, alright? So question 13. What could the last digit of fourth power? Basically, it's just the same logic. And we test all form of this to the power of 4. And the k is the number that's tailing the 10n. And we make a whole table and we find all the modulo of 10. And this is what we get. And this could be only equals to 0, 1, and 5, and 6. Next. Question 14. Show that the difference of two consecutive cubes is never divisible by 3. We're just gonna take a look at all 3 different scenarios about modulo 3, and we find that they are all equals to 1, which is very interesting. Not only it is never divisible to 1, it can also not be any form like 3k plus 2. It can only be 3k plus 1 based on the result we have here. And similarly, question 15, we're just going to take a look at modulo 5. And if none of those numbers equals to 0, which means they cannot be divisible by 5. And let's flip the page. This is going to be the last page, I believe. Never mind, we have question 20 just behind those pages. I'm sorry. So question 16. So show that the modular 11. I think you might have heard about this. If we rewrite the base 10 to the power of k, rewrite it like this, 11 minus 1, and the remainder is just going to be based on minus 1 to the power of k. And if k is odd, then this is equal to negative 1, which is congruent to number 10. And if this is even, then we can be certain that it can be congruent to the number 1 modulo 11. Yeah, I think it's not too hard to understand from here to here, right? Hopefully. And question 17. By using our conclusion in 16, which is this alternating things here, and we're gonna calculate this, and we find that the alternating series is equal to negative 22, which is a multiple of 11, which means that student A is correct and B is wrong. And question 18, every palindrome, we need to prove it is divisible by 11. First, we know that the palindrome is the same reading, it's symmetrical about its center, which means what the left hand side should equal to the right hand side, which means it can be expressed as some form of this: 1001 A plus 110B, and those two numbers are both multiple of 11, which means the overall thing is also divisible by 11. And the part B, how about the 6-digit palindrome? And similar logic, we find that those three numbers are both multiple of 11, which is that the 6-digit palindrome is also guaranteed to be a multiple of 11. And question number 19. So show that if 9 congruent to 9 modulo 9, congruent to 4 modulo 9, n cannot be written as the sum of 3 cubes. So we make a table and find out all the remainder about the cubes modulo 9. We find that it could be only those numbers. That means that we have to pick 3 numbers from the set, and we're gonna form a sum. But by trying this, we cannot find any combination of sum that form a number which is congruent to the number 4 modulo 9, which means that no sum of 3 cubes can have n congruent to 4 modulo 9, and thus the conclusion is being proved. And question 12. This one is actually very interesting. I spent quite a lot of time when I first reading this question, and I eventually get it. I'm very proud of myself, and if you don't get it, it's alright. And as you get better and better at math, you're gonna be more capable dealing with those difficult and complex questions. It's no shame to not knowing how to do a math problem. You know, I used to be very bad, but I'm getting better, I'm improving. So this question, we're gonna prove that if x is congruent to 1 and to the modulo m to the power of k implies that x to the power of m congruent to 1 modulo m to the power of k plus 1. So first thing first, from the first congruence, we can know this, and we can rewrite x to the power of m minus 1 can be rewritten as factor form like this. And this has a factor of m to the power of k due to the first congruence. And all we have to prove is that this thing is actually a multiple of m. So we can reduce this congruence here to this. And we know that x to any power it's going to congruent to 1 modulo m. And it is just like this. And there is a total of m term, and each one of the term is congruent to 1 modulo m, which means they are divisible by m. Thus, we are done with our proof. So this is divisible by m, this is divisible by m to the power of k, which their product should be divisible by x to the power, m to the power of k plus 1. And that concludes our section today, and I hope you enjoy this video, and hopefully the next video will coming up soon. And thanks for watching. Goodbye.